Hi physics students, so we are working on Unit 6, Worksheet 1, and we are starting with the sketch of a transverse wave. This is what we call a transverse wave, and what we need to do is measure the wavelength and the amplitude. So if you remember, the wavelength can be measured multiple ways. It can be measured crest to crest, it can be measured trough to trough, or you can measure from the center or equilibrium up, down, and back to equilibrium. So however you decide to measure it is up to you. You should get this exact same value no matter what method you choose. So based on my ruler and my calculations, I got a measure of 3.9 centimeters. You might get something slightly different based on how you estimated it, but it should be around 3.9. Now the amplitude, you can measure this also several ways. First of all, you want to take an equilibrium point. So let's say that's my equilibrium. Actually, it looks a little bit too low, so let me see if I can move it up a little bit. That looks a little bit better. Again, this is an estimation. Do as best you can to figure out where your equilibrium would be, and then from there, you can measure from your equilibrium point up to your crest or your equilibrium point down to your trough. So whatever method you choose, as long as you estimated it relatively correctly, you should get around a value of 1.3 centimeters. Okay, directly on the sketch above, identify one crest, one trough, and illustrate the amplitude. So here's my amplitude. I've got a crest here. Let me use a different color. This would be one crest, and this would be one trough. The next question says, sketch a wave below that has a wavelength of approximately half that of the wave shown above. So basically, if we're trying to sketch something with a wavelength half, that means I would need to have two crests within one crest here. So I'm just going to use a highlighter. Again, you're eyeballing this. So I'm going to say between trough and trough, I'm going to have two crests in between there. So as best I can, I'm going to draw two crests within a trough, another one about the same size. That would be example of a wave with half of the wavelength. Okay, the next question shows us a slinky where we've got a longitudinal wave this time, and that means it's traveling left and right, and we want to identify compressions and rarefactions. So compressions are pretty easy. They are the points in which the slinky is compressed. Rarefaction would be the other point where it is stretched. And then we need to measure the wavelength of a wave. So you can do this multiple ways. You can go from the middle of your compression to the middle of your compression. I feel like that's the easiest method. Or you can go from the middle of a rarefaction to the middle of a rarefaction. And again, that should be about the same distance. So if I measure this out, I get a value of about 4 centimeters. If you get something around there, your estimate might be a little bit different, but it should be around 4 centimeters. Okay, in this next question, it says, in each of the following situations, two pulses are shown traveling toward each other. Make 3 sketches showing what will happen just prior to, during, and immediately after intersection. So what we know about waves, when they come together, the amplitude actually adds together. So this is just before. I'm going to show a wave like that, and then right below it is the wave. This is just before they come together. When they do come together, they actually cancel each other out because they have about the same amplitude. One is above in the positive, one is below in the negative, so they would cancel out to 0. And then as they go through each other, the wave that is in the negative direction is going to now pass the wave that is in the positive direction. So it'll look something like this. Okay, so for this, we've got a wave with a large amplitude and a wave with a small amplitude. Right before they come together, it would be the large wave right next to the small wave. And then when they actually add up, you'd have the large wave extra big in terms of its amplitude because they're adding together. And then when they go through each other, the small wave passes the larger wave, so it would look like this. So that would be your second scenario of waves interacting, or what we call adding together. And in this next example, we've got two students holding an end of a slinky, and they are 5 meters apart. So that's their distance. It takes 6.6 seconds for a transverse pulse to travel from the student, generating the pulse to its lab partner at the opposite end. How long will it take for the reflected pulse to return to the generating student? So the speed in which a wave travels, as long as there's no energy loss, should be the same on the way there as it is on the way back. So same speed, back, 0.6 seconds. When a second pulse, twice the original amplitude is sent, will the pulse take more time, less time, or the same amount of time? So it's going to be the same time because amplitude does not affect wave speed. Now the student moves so that they are now further apart but use the same spring. Compare the speed of a pulse on a more stretched spring to the speed of a pulse when they are 5 meters apart. So we learned this in our lab, that the greater the tension, the faster the wave travels. So in this case, it's going to have a higher speed. And then the student moves back to their original separation. The generator produces a longitudinal pulse in the spring. How does the speed of this pulse compare to that of the transverse pulse? Again, we learned this in our lab, that a longitudinal wave travels faster. So it's going to have a greater speed, greater wave speed. All right, so that concludes this lab, that concludes this worksheet. If you have any questions, contact your teacher.